Hi, this is Ashwini Dashgupta from Chitta.com. Today, we have a very exciting topic from geometry, from Math Olympiad geometry. It's known as the Vecten configuration. Now, I will discuss more about it in an upcoming seminar on mathematical Olympiads. If you want to register for it, check the link in the description and you can join our WhatsApp group and get all the details. What is the Vecten configuration? It's a generalization of one of the proofs of the Pythagoras theorem, one that is prescribed in the earliest books of geometry, for example, by Euclid. I will draw the configuration for you and then discuss one interesting property. So let's see how that goes. We start with any triangle. So let me draw a triangle. It could be a scalene triangle. That's totally fine. And then we will draw squares on three sides of it. It won't be perfect, but it will be like an approximate square. And then we have a third square, which is on this side. Okay. Now, this particular configuration, this picture that I have just drawn, is known as the Vecten configuration. And there are many beautiful properties of this. If this base triangle is right angle triangle, you can use this configuration to prove the Pythagoras theorem. But today we will see one other property which also involves rotation. To solve geometry problems from mathematical Olympiads, rotation is a very powerful tool. I have discussed it over and over again in Chitta's Math Olympiad programs. You can check such programs in the link in the description for more details. So let's see what this flank triangle property is. Flank triangle. So let me write that. Flank triangle. So what are the flank triangles? So it's very simple. I'll draw them in green. Here is a flank triangle. And we have here a flank triangle. So we have three flank triangles given the Vecten configuration. And we can show that these flank triangles are equal in area with the original triangle. Original triangle is the triangle in the middle. This one. This triangle. So each of the flank triangles is equal in area with the original triangle. And we can do this using a rotation. So let's see how we can sort of prove this theorem using a rotation. So let me write it first. Each flank triangle equals area of original triangle. That's what we want to show. Now notice very carefully what I do here. Okay, it's so fun. What I'll do is, I will rotate, let's say I want to work with this flank triangle. I will rotate this flank triangle by 90 degrees and I'll see what happens. Okay. So let's first go ahead and delete the squares. So I just delete the squares so that I just have the flank triangles. Okay. So now I've deleted the squares and now I will rotate the flank triangles about the vertices. So I will rotate this one by 90 degrees, this one by 90 degrees, and this one by 90 degrees. Okay. So what happens if I do that? Well, first notice that this side will exactly fall on this one. Why? Because these two sides are equal in length, right? Because it's a square, it was a square built on this side. So these two sides are equal in length. So they will fall exactly on the top of each other if I rotate by 90 degrees. So now let me draw the rotated figure in red. So I have this side falls by 90 degrees. This also goes by 90 degrees. So I have sort of like this. So this was 90 degrees. So it goes here in a sense. And then I have to join these two. So there you go. I have rotated this green triangle by 90 degrees. Whenever you are doing a problem related to rotation, you have to think about the center of rotation and the angle of rotation. Two things. Okay. So here the center of rotation is this point here and the angle of rotation is 90 degrees. Okay, let's give names to the original triangle A, B, C, and let's give names to this one. So this is X and this is Y, suppose. So now AX was making 90 degrees with AC. It turned by 90 degrees. So you have X prime here, X going to X prime. And similarly, Y goes to B, which is also Y prime. Right? B is Y prime, image of Y. We are almost done. Now first notice that this is a straight line. Why? Because this was 90 degrees and you rotated by 90 degrees, so total 180 degrees. So this has to be a straight line. Secondly, since AX is equal to AX prime is equal to AC, so we have AC and AX prime equal. AC and AX prime equal, right? So now what do you have? You have a big triangle in which half of it is the original triangle ABC and half of it is the rotated triangle AXY, the flank triangle. You see what just happened? You rotated the flank triangle by 90 degrees and now you have a big triangle. Half of it is ABC and half of it is the flank triangle. Isn't it wonderful? Therefore, these two triangles are equal in area. So this is one example of properties of the Vecten configuration. There are many such beautiful things built around this configuration. I will talk more about it in an upcoming seminar. You can join our community for free. Check the link in the description for more details. There is a form which you can fill up and then you'll be redirected to our WhatsApp group. Stay well and keep on doing great mathematics. I will see you in the next one. Bye.